This is the introduction to alternating current. Here in the name alternating current, we have this word which is the alternate, and this alternate word mean the change. So the alternating current mean that those current which change in magnitude and direction. And here in this lecture we will discuss in more detail about the alternating current, which is a change in magnitude and direction. So for the reference we have to discuss the direct current. So for that we have this simulation. In this simulation we have the simple circuit which consists of this battery, and this is the switch, this is the bulb, and this is the emitter. Here these all components are connected with each other through this conductor. Okay, so this current supplier, this current supply is actually the DC. Current supply is the DC. DC means the direct current. So now we will see that what will be the behavior of electron inside this conductor if we provide the DC. So here I am going to turn on this switch. Okay, so the current will start motion in this conductor, and here if you see the direction of the electrons, the flow of electron is in one direction. Okay, so it is actually from the negative terminal of this battery to the positive terminal of this battery. Okay, so this is the behavior of electron if we provide the current, if we provide the DC source. Okay, so what will happen if we provide the AC source to this same scenario? Then in that case this electron will not flowing in one direction. Every electron will be vibrating just like the simple pendulum. Okay, it will vibrate from its mean position, and this electron will also vibrate from its mean position. Each and every electron present in the conductor will vibrate from its mean position. It will achieve the maximum value, then it will become 0. It again will be come to the maximum value. Okay, so that's the behavior of the simple pendulum. So why this electron is behave as a simple pendulum mean that it vibrating about its mean position. So the reason behind that is this in alternating current, as the name indicate, the alternating mean it will change its direction and as well as its magnitude. So here if we provide the alternating current, this side will become positive and this is negative. Again this will be positive, this will be negative. Okay, then this will be positive, this will be negative, then this will be positive and negative, and this flipping of this charges, this flipping of these polarity will be occur 50 times in a second. Okay, so it means that when if this side become for the in case of the AC current, if this side become the negative and this is the positive, the current will start motion in this side. So electron will be flow in the upward direction. So here this electron will be flow in the upward direction. But again here the polarity will be changed in case of the AC. So this side will become positive. Okay, and this will become negative. So again the current will flow in this direction. Now this same electron will be flow in this direction. Okay, so similarly again this polarity will be changed, this will become positive, this will become negative, and again the same electron will start motion in this direction, and this polarity if change again. Okay, then it will the electron will start motion in this direction, and in this way the electron will be move in this direction. So this is actually the represent the vibration nature of the electron. It will vibrate about its mean position. So at the mean position its magnitude is 0, at this position its magnitude is more, at this position its magnitude become higher, and at this position its magnitude become maximum, and again its magnitude is decreasing, and here at the here at the equilibrium position, okay, its magnitude becomes 0, and here it will again increasing in the negative side, okay, and it become maximum in the negative side. So we will discuss this in more detail. So what I am going to mention here is that if we provide the DC current, the electron will start motion in one direction, and if we provide the alternating current, the electron will start vibration about its mean position. Here in this simulation we have that same scenario. Here we will provide the DC. Let's say first I am going to provide the DC source here. So this is about 1.5 volt DC source, and I am going to disconnect this, okay. So here in this case, if we provide the DC source to this this circuit, okay, the electron will flow from the negative terminal of the battery towards the positive terminal of the battery. So here is this red color is actually that conductor, and this is the direction of the current. And here if I zoom this conductor, it will look like this, okay. So inside this conductor, these free electron will be these free electron will be moved in this way, okay. It will be moved from the negative terminal of the battery to the positive terminal of the battery, and this is the direction of that electron. If I increase the voltage of this DC, so this is if I increase this to the 9 volt, their motion will be increased, and this will be glow up, okay. So the magnitude will be increased, but the magnitude will be remain constant throughout here, because this is the direct current. In the direct current, the direction will be constant and the magnitude will be also constant. So in this case, the direction is constant, the electron always flowing in from the left to right in this case, okay. And the magnitude is constant here is there because this bulb do not show the flipping here, okay. So it is not become dim and then again it glow up, okay. So this is at one position. And what will happen if we provide the alternating current? So as we know, alternating current is changing in magnitude and also in direction. So I am going to provide the alternating current here. So in case of the alternating current, the electron will vibrate about its position, its mean position. So here each and every electron is vibrating about its mean position, and we discussed the reason behind that, because here this polarity is changing. So within 1 second this polarity is changing 50 times, okay. So it means that 50 times this side become positive, this will become negative. So if this side become positive, the electron will start flowing in this direction, and here the electron in this case, okay, the electron in this case will move in this direction, okay. So if this side, if this side become positive and this become negative, okay, this is the alternating source, then the electron will start motion in this direction. Now if this become positive and this become negative, again that same electron will flow in this direction, okay. So if this direction again flipped, okay, this if this become negative and this become positive, the same electron will again flow in this direction. And here if this become positive, this become negative, that same electron will now flow in this direction. So in this way, here in the alternating current, the polarity is changing many times, about 50 times in a second. So therefore this electron is vibrating about its mean position, okay. It's vibrate about 25 times, okay. So it means that this electron will move in this direction for the first polarity, okay. If the polarity is again changed, the electron will be moved in this direction. So here the polarity is changing 50 times. So this cycle would be 50 times. Okay, so this is the reason behind their vibration. Now we have the other simulation. This simulation is actually representing the process occur in the powerhouse. In powerhouse, we have this water which is falling from the higher height towards the lower height, and this water will have more potential energy. That potential energy will be used to rotate this turbine, and here and with this turbine we have this magnet, and due to which the change in if this turbine is rotating, the magnet is also rotating, and due to the rotation of this magnet, the change in polarity of the change in the direction of the magnetic field will be occur. So according to Faraday law of electromagnetic induction, the change in magnetic field will induce the electric field. So here if we bring the coil inside that the region in which the magnetic field is changing, the electric field will be induced in this the conductor of the coil. So here that electron, due to the change in polarity of this magnet, will be vibrate about its mean position. So the alternating current is produced in such a way. So here this electron is vibrating. So and in this way, if we connect the bulb to this coil, it will be glowing up, and then it will become turned on, and this will become turned off. Okay, so when the electron is at mean position, this bulb will be turned off. Okay, so if this electron is moving at extreme position, then this bulb will be glow more. Okay, so in between that mean and extreme position, their dim and their intensity, the intensity of this light will be more. Okay, so here this electron is vibrating about its mean position. Due to its vibration, the magnitude of this current is changing. Okay, and also due to the change in magnetic external magnetic field, this induced EMF according to Faraday law of electromagnetic induction. Okay, so now according to the Lenz's law, this induced EMF will always oppose the change it produces it. So here it will oppose the change in magnetic field, and this electron will also vibrate due to their opposition. So here this electron is vibrating, and it produces the alternating current. Okay, and this alternating current is changing in magnitude and direction. So here we have that same scenario in the this is actually AC generator, and here we have this north side, and this is the south pole of the magnet, and between these two magnet we have the coil, and that coil is vibrating. So when the conductor is vibrating inside the magnetic field, an EMF will be induced in that conductor, and in this case, in this side of the conductor, the current will be flow. Okay, and that is given by the Fleming right hand rule. And here on this side of the conductor, the same current will be flow, but with the opposite direction. So therefore here the current will be produced, and that current will be changed in magnitude and direction as well. Okay, so here therefore if we connect that with the any galvanometer, let's say here is a galvanometer, their needle will be deflected, and it will become increase and decrease, and here this is the mean position, so it will vibrate about its mean position. And here if we find if we draw the graph of that change in the polarity of the voltage or the current, then it will give us the sinusoidal wave. Okay, So this at this position it becomes 0, then it attain the maximum position, and then it becomes 0, and again attain the maximum position at the inverse, and then it becomes 0. So in this way it produces the sine wave. And here the frequency will be if I increase the frequency, it means that I increase the turning of this conductor, the rotation of this conductor inside the magnetic field. Okay, and here in this graph the frequency of this sine wave will be increased, and here this frequency become more, and this rotation also become more, and here this deflection become more, and therefore we call that the AC current is more. Okay, so it means that the AC current is changing its magnitude and direction many times in a second. Okay, so up to here we differentiate little bit between the alternating current and the DC current. Okay, so in this lecture we will only focus on the alternating current. So we have that same scenario. This is the south pole, this is the north pole, and the magnetic field line will be originating from this north pole of the magnet, and that will be terminating in this south pole of the magnet, and inside this magnetic field we have this coil, and this coil is rotating. Okay, due to their rotation the change in magnetic field will be occur according to Faraday law of electromagnetic induction. Due to the change in magnetic field will leads to induce EMF, and here the current will be induced in the conductor of this coil. In this side of the conductor the current will flow from the bottom to the top, and here according to the Fleming right hand rule that current will be flow from the top to bottom, and that current is collected by the slip ring and the carbon brushes, and that is provided to the towns or to our home that we will use in our home for turning on the fan or the TV or other home appliances. Okay, so we have that same scenario, and we are going to hear that how this AC current is producing. So this side is the north, this is the north pole of the magnet, this is the south pole of the magnet. The magnetic field lines are originating from this north south, and from this north and terminating on this south. Okay, and inside this magnetic field we have this rotating coil, and this is actually the snapshot of that rotating coil at different positions. So this is actually the snapshot of that coil which is at this position. Okay, and this coil is at this position, mean horizontal, and this is again become vertical, and this is become horizontal, and this is become vertical, and in this way it completes one rotation. And here is the graph for that one rotation. So when the coil is perpendicular, so when the coil is vertical here, the change in so the flux here will be, so here the angle, the area of this side of the coil will have some direction, and that direction is outside from the screen. Okay, so this is the direction, and here the direction is from left to right. So here the angle theta is equal to 90, and magnetic flux is equal to B A cos theta, and cos 90 is equal to 0. So therefore the magnetic flux here is 0. So when the magnetic flux become 0, then according to the Faraday law of equation. Okay, so in that the change in magnetic flux will leads to EMF. So here this magnetic flux is 0, so the EMF is also become 0, and it give us this position. Okay, similarly in this second position we have that coil is horizontal, and this side of the coil will have some area. The direction of that area is this, and the direction of external magnetic field is this, and here is the angle theta is equal to 0, and the magnetic flux will be present here. Here the magnetic flux will be a maximum, and hence the induced EMF will be maximum according to Faraday law of electromagnetic induction. And similarly again we have that same coil, but now its position again to vertical, and again here this theta become 90, and theta, when the theta become 90, the magnetic flux becomes 0, and hence the EMF becomes 0, and it give us this position. And here this again become horizontal, and the theta is equal to 0, the magnetic flux will be maximum, and similarly the EMF, the induced EMF will be also maximum, but in opposite direction. So here this opposite direction is actually given us by the Fleming right hand rule. Okay, now at the last position this coil again become vertical, and here the angle theta is equal to 90, the magnetic flux will be 0, so therefore the induced EMF become 0. So now what is now if I connect these points, okay, so this is the first point. If I connect these, okay, it give us such like shape, and we call this graph is a sinusoidal wave. So it form the wave like shape here. So this wave is called sinusoidal wave. So here the question arises that if here we only plot these data points, okay, then how we connect this with this in this way? Why we don't connect this in this way? Okay, this directly, why we don't connect this in this way? So the answer for that is this. Okay, so I'm going to rub this. Okay, so the answer for that is this. So for the first degree we will have some magnetic flux value and EMF value. So for the second degree we will have some EMF value. Similarly for the other degree we will have some EMF value, and therefore we will have about 90 EMF value, instantaneous EMF value for each data point. And if we draw that, it will give us the sinusoidal wave. Okay, so here is that simulation. Okay, here we have this same scenario. This is the north pole of the magnet, this is the south pole of the magnet, and between these two poles inside this magnetic field we have this coil, and this coil is at different position, and here that coil is represented by these lines. Okay, when the coil is the 0 position, so it represent here, this is become 45 degree, it become 90, and about 45 degree is changing. Okay, so for each as I have discussed, for each degree change there will be change in the induced EMF. So here for 0 degree it give us this EMF value, for 45 degree it give us this EMF value, for 90 degree it give us this EMF value, and similarly for 135 degree it give us this EMF value, and this is for 180 it become 0. So this is actually the EMF values. Okay, and the vertical axis and the y axis we have this EMF value, and again for 225 it give us the EMF value but with the negative sign, and which is given by the Fleming right hand rule, and here at 270 it become again maximum at the negative side, and in this way this alternating current is changing its magnitude with time. Okay, and this is the change in magnitude, and here this upper side, okay, this graph above from the mean position is representing the positive, and this graph is below this mean position representing the negative. And here in one cycle, one time the flipping of these poles will be occur. So here the change in the direction of the alternating current is occur due to the flipping of these terminals, and the change in magnitude of the alternating current is occur due to the change per degree rise for degree rise, and here for each degree we have different EMF values. So therefore their magnitude is changing with the degree. The magnitude of the induced EMF is changing with each degree rise. Okay, so therefore their magnitude is changing. Okay, so in this way the magnitude is changing and the direction is also changing in alternating current. And here we have that same scenario. So if this is becomes 0 at this position, the EMF is 0. So for the I1, okay, this is actually the instantaneous value I1, the EMF will be this, and for I2 the EMF will be this. So here let's say this is actually the current, and we also consider it as a EMF, the alternating EMF. Okay, and this is actually the alternating current. Both are changing in magnitude and direction. So for the both the graph is the same. So here this is for the I3. So for the I3 the EMF is this, for the I4 the EMF is this, for the I5 EMF is this, for I6 EMF is this, and for I7 it attained the maximum value. Okay, so for this I1 is actually the current induced in the conductor present inside the magnetic field at this degree, and the x-axis we have the degrees. Okay, so on this second degree, okay, on this degree that EMF will be different, and this degree that EMF will be different, and this degree that EMF will be different. At degree is equal to 90, that EMF will be maximum. Okay, and at degree is equal to 91, that EMF will be decreasing here. Okay, so at this position, if we increase this angle from 91, 92, 93, 92, and here it will be give us these instantaneous values of the alternating current and alternating voltage. And if we reach this 180 degree, their EMF, alternating current and alternating voltage become 0 at 180 degree, and above that 180 degree the same process will be occur but with the opposite direction. Okay, and therefore we consider this side as a negative and this side as a positive. So from here we conclude that the DC current do not change its magnitude and direction. Okay, but the AC current is changing its magnitude with each degree. Okay, and their direction is also changing. Okay, and the direction and when in the circuit, when we provide the DC supply to a circuit, the electron will flow in one direction. Okay, in one direction from the negative terminal to the positive terminal. But if we provide the alternating source to the circuit, the electron will flow in the sinusoidal form, mean that it will vibrate inside that conductor. Okay, it will vibrate about its mean position. It will attain the maximum value, then it becomes 0, and then again it will attain the maximum value. Okay, so that vibration of the electron inside the conductor is due to the change in the polarity of the alternating current. As we know, in most countries the frequency of alternating current is 50 Hertz. It means that 50 times this current will change its polarity. It means that electron will be vibrating about its mean position. Okay, due to the change its polarity. Okay, and their magnitude is also changing. When the electron is at mean position, their magnitude will be 0, and if it going towards the extreme position, their magnitude will be changing. Okay, for each small distance. Okay, so this is the in-depth intuition of the alternating current and the DC current, and this is the difference between the alternating current and the DC current. So that's it guys, thanks for watching.